Okay, what about this? So a hunter, we got to kind of orient ourselves a little bit here. So a hunter is at a point along a riverbank. So there's the hunter, H. He wants to get to his cabin, which is located 4 miles north and 10 miles west. So he's going to have, the river just goes east-west here, right? Everybody see this? So he's going to have to go 10 miles west and 4 miles north. He can travel 5 miles per hour along the river, but only 2 miles per hour on the rocky land. So the question is, where should he leave the river to minimize the transit time, to minimize the time it takes him to get to his cabin? You understand what the options are? Like if he were to strike off immediately, leave the river, and strike off across the ground, that's probably not a good idea. How come? Because he goes so much more slowly on the ground, right? But he also probably doesn't want to go 10 miles over along the river and then have to go 4 miles up, because that's too long a distance. And again, that's probably not the shortest route. So somehow we've got to come up with an objective function here in terms of some variable that we'll define, probably x, right? That's going to tell him where does he need to leave the river. Okay. So what do you think? Ideas? What could my variable be here? And before we even talk about that, how are we going to get time out of this? Let's just talk about, how is time going? How is that related to the stuff in this problem? We've got some speeds or velocities, right? How is time related to speed or velocity? Okay, velocity equals distance over time, doesn't it, right? Okay, so then we could do something like, if we want to talk about the velocity along the river, we could do something like this. We'll just call it V sub r, for the velocity along the river, is just going to be the distance that we cover along the river divided by the time that we spend traveling along the river. Agreed? Now we're interested in minimizing the time, so we probably want to write that equation where we're solving for t, right? If I were to isolate the t, what do we get? The time along the river is equal to what? Yeah, right. Time is, distance over velocity, exactly, right? So the distance along the river divided by the velocity along the river. And using similar logic, if we were to talk about the time across the land, what would that be? I mean, the math's the same, just the subscripts are different, right? The time it takes to cross the land would just equal the distance across the land divided by the velocity across the land, right? Would you agree? Okay, now we know what the velocities are. They're 2 and 5. Okay. Only things we don't know here in those equations are the distances, right? So we know that the time along the river is just equal to the distance along the river divided by 5, because that's his speed along the river. And the time along the land is the distance along the land divided by 2. And the total time would just be the sum of those two things, wouldn't it? If we break the trip into 2 parts, time along the river plus the time along the land is the total time it takes him to get to his cabin, right? Give me thumbs so far, is that good? All right, so then the parts that we need to fill in are these parts. Okay, so we're going to need a variable here. Where could I attach the variable to my picture? What do you think, Aubrey? I can see you had a good idea. I can tell.
That side of the triangle.
So this side of the triangle right here, or this side? Okay, if I use that side, that's going to make things complicated, right? Because if I make this, let's just audition this idea here, and let's see what we think. If that's x, then this is going to be a fairly complicated distance right there, isn't it? It's going to involve square roots. And the distance that he travels along the river, isn't that just going to be 10 minus whatever that distance is corresponding to that bottom leg of that triangle. Everybody agree? Okay, so let's backtrack a little bit. Can we think of maybe a more convenient, that would work. It would work, but it's just going to make the math complicated. Can we think of maybe an easier version of x? I mean, we could put it there, couldn't we? Right? And that makes sense in a way because x would represent, if it's this distance right here, x just represents how far is he going to go down the river before he leaves the river and strikes off cross country, right? That would work. What would that make this distance along the bottom of the triangle?
10 minus x.
10 minus x. Okay. Unfortunately, that makes the hypotenuse kind of complicated, doesn't it? Do you see what I'm saying? I mean, it would work, but the hypotenuse is going to be the square root of 4 squared plus, here, let's just write it down. The square root of 4 squared plus 10 minus x squared, right? Everybody agree? That's kind of complicated because I've got a square root involving all kinds of crazy stuff, right? This would be fine. It would work, but can anybody propose maybe even a slightly improved version of this? What could we do that might make it a little easier? Yeah, right there, right? What if we let that be x? That might be easier. Okay, let's go back and erase all this stuff. So finally, I think we arrived at the easiest way to set this up. If we let the bottom leg, that horizontal leg of the triangle equal x, then what does that make this distance? 10 minus x, good. So that distance from there over to there is 10 minus x. And that makes the hypotenuse of that triangle a little simpler, right? Everybody agree? So what is the hypotenuse going to be? By Pythagorean theorem, what would the hypotenuse be if that leg is 4 and that leg is x?
Square root of 16 plus
X squared, right? Yeah. So square root of x squared plus 16. Yeah, that makes sense, doesn't it? We get a little easier square root to deal with. We don't have x squareds and x's and all that kind of stuff underneath our radical value. Okay. Is this x quite as meaningful? Maybe not. It's probably, ideally, it would have been nice to have x be the distance that the hunter's going to travel along the river. But if we solve for x, 10 minus x is pretty easy to solve too, right? So once we know the value of x, we ought to be able to figure out where he leaves the river pretty easily. Okay, give me 1 to 5. Is that how we do it so far? Okay, questions? See if you can ask a question, somebody. Put you on the spot. Like, what part of this is not making sense? We get this idea, right? That the time, these are the equations for the time along the river and the time along the land. So the total time then, is just going to equal T sub r plus T sub L. Time along the river plus time across the land, right? Okay, problem being, we don't have that in terms of a single variable yet. We've got 2 variables there. I have d sub r and d sub L, and I want 1 single variable. Well, the single variable we defined as x. And now I've got the distance across the land written with x's, and I've got the distance along the river written with x's in terms of x, right? And so I could write my time equation out with only a single variable. Okay? So what's this give us then? This gives us total time is equal to T sub r, which is just going to be the distance along the river. Well, that's 10 minus x over 5, the speed along the river, plus the distance along the land, which is that square root expression, over the speed across the land, which is 2. And there's my total time as a function of the variable x. Okay. Everybody see that? See if you can make a prediction here. What's going to happen to this point, the position of that point, as the distance across the land gets really slow? Where's that going to move the point? Further to the right. Okay. As the distance across the land improves and gets closer to the distance along the river, that's going to drag the point over this way a little bit. Everybody see that? We just need to figure out which, ask my wife. I don't know what's going on. 1 second. So there's our objective function of a single variable. Does that help? How are we doing? Give me 1 to 5 now. I'm just curious. Be honest. That's supposed to be 3.5?
Yeah.
Okay. Okay. Things are okay. All right. Things are improving. That's good. So we got our objective function of a single variable. What's our domain going to be? I mean, there are no restrictions on the domain that you can obviously see in the function. Well, actually, there are. No, there aren't. There are no restrictions, right? Because inside the square root, there's no value of x that's ever going to make that negative. And there's no x's in denominators, right? But if we look at the picture, there are some values. I mean, like we could kind of determine, okay, the minimum value x could ever possibly be would be what? 0. Yeah, which would mean if that were 0, that would mean that the hunter traveled all the way along the river. It would make absolutely no sense to go further than 10 miles and then backtrack, right? We can just ignore all those options. 10 would be logically the biggest possible value we would ever consider, just traveling all 10 miles along the river, which corresponds to x equals 0. What's the biggest value x could be? What's the biggest, what would be the maximum length of the bottom of that triangle that would possibly make sense? 10, yeah, which would mean that the hunter leaves directly from where he starts, which we already know that's probably not it either. But that would be the only domain we would need to consider. Okay? And now this just becomes, we can flip into calculus mode, and this is just a table problem, isn't it? Right? Okay, so what would we do? Been a little while. We had some vacationing going on here recently, so see if we can get back on track.
Take the derivative.
Take the derivative. There you go. Good.
Oh no.
So t prime of x. Okay, well, this first, I mean, really that first one, we could even write that if we wanted to as 10 over 5, which is 2, minus x over 5 plus square root of x squared plus 16 over 2. That might help a little bit, right? Okay, so what's the derivative of this part going to give me?
What?
What's the derivative of that part going to give me? If I split the fractions, it makes it easier. What's the derivative of 2? 0. What's the derivative of negative 1/5 x? Because that's how you want to think about that, right?
1/5.
Negative 1/5, exactly. So we get negative 1/5. And now here, this is going to be a little more complicated, right? Because we've got an x squared plus 16 to the 1/2. So we're going to have to use chain rule on that one. So what's the derivative of this part going to give me? Plus, I can pull that 2 out front, right? I've just got a 1/2 there. I'll just leave that out front. And then what's the derivative of x squared plus 16 to the 1/2? Right? Because remember, all that is, this is the same thing as saying 1/2 x squared plus 16 to the 1/2, right? So what's that give me? The power is going to be negative 1/2, right? What's the first step? If I've got hand to the 1/2. What's the derivative of hand to the 1/2? 1/2 hand to the negative 1/2, right? So I've got my 1/2 that's already out there times another 1/2 that comes from the exponent times hand to the negative 1/2 times the derivative of hand, which is what? 2x. Yeah, there you go. Okay, so then what's that give me? I get t prime of x equals negative 1/5. I could do a little cancellation here, right? I could cancel one of those 1/2s with that 2, and I'm going to get negative 1/5 plus, let's make this a fraction. So I've got an x in the top, and on the bottom I'm going to have a 2 times the square root of x squared plus 16, right? Everybody agree? Okay, are we going to want to take a second derivative here? Heck no. Why would we, right? We've got radicals in this. No way. So we're just going to use the first derivative test. We're not going to, because we don't need the second derivative. All we need to find is the maximum, or the minimum, right? Minimum value. So we really don't need a second derivative for that. If it's convenient to do, yeah, we would use the second derivative test because it's so simple. But when the derivative is complicated like this, yeah, we don't want to fight this anymore. We don't want to take a second derivative. We'll just pick test points on either side of our critical number if we find a critical number. Agreed? Okay, give me 1 to 5 on that, what I just said. Does that all make sense? Why strategically, first derivative test would definitely be the call here, right? So now we just need to know where the critical numbers are, okay? So on our domain, where would t prime equal 0? T prime equals 0 when that second term is equal to 1/5, isn't it? Everybody agree?
Yeah.
Okay. So we just have to solve that equation. What do we do?
The fraction.
Yeah, I mean, I've got a ratio, right? So I could just cross multiply to get rid of the fraction. Everybody agree?
Yeah.
First cross product's going to give me 5x. Actually, let's do this cross product first. So this cross product is going to give me 2 times the square root of x squared plus 16. This cross product is going to give me 5x, and I just have to solve that radical equation. So think back to last year. What'd you guys do to solve a radical equation?
You inherited it.
What'd you do? You square it, don't you? Right? Because we want to undo the radical, right? So we want to undo the square root by squaring both sides. But remember, when you square both sides of an equation to get a solution, you possibly introduce extraneous solutions. So that means you have to always check your answers in the original equation to see if they work. Right? Remember that part? Okay, so we're gonna change colors here. We're gonna all of a sudden go to red because when we square both sides, that's gonna give us, well, that's not red. We're gonna go to, like I said, we're gonna go to red. The 2 squared gives us 4. Square the square root and we get x squared plus 16. On this side, we're just gonna get 25x squared, right?
Yep.
Okay, so then if we distribute the 4 and collect like terms, we're going to get 64 over here, and I have 4x squared, which I'll subtract from both sides and get that, right? Make sense? Okay, so if we isolate the x, we get x squared equals 64 over 21. And so if I square root both sides, x is equal to plus or minus the square root of 64, which is 8, over the square root of 21, right? Well, do we want both of those?
No.
Only the positive one, because that's the only one that's in our domain. Okay. So we get x equals 8 over the square root of 21. Well, we would need to go back and check that in the equation before we squared both sides. So we would take that result, and we've got to go plug it in there and there. And what would happen if we did that? We would get 2 times x squared in this case would be 64 over 21, wouldn't it? Everybody agree? Like that's going to be, if I square that number, I just get 64 over 21. So I get 2 times the square root of 64 over 21 plus 16 on this side. What about the other side? I get 5 times 8 over the square root of 21. So we just need to see if that works. Okay, well, does it? Let's see. We're going to get 16. We would have to multiply this guy by 21 over 21, right? Okay, let's just do this. Just to save a little time here, just plug those in calculators. And let's just see what our decimals are. If our decimals agree, which they're going to, then that's a valid solution. So what does this left side become if I just evaluate that as a decimal? Uh-oh. Where's Carson? He's supposed to be here to do this stuff on a calculator. That's his job. I think I have decimals pulled up here somewhere. She's getting it?
Yeah, they're the same.
They're the same. Okay, what are they?
8.7287.
Which is equal to, same thing on both sides, right?
Yeah.
So we get the same thing, so that is a valid solution. Okay, that's our value of x that's going to work. And so now we would just go back and build a table with that, right? Let's make a table up here. It's getting kind of messy. Our input variable was x. Our output variable was t in the meter row for t prime. Okay, what did we say? X is going to be pinned between 0 and 10. And what is as a decimal? Let's just turn this into a decimal rounded to 2 places. What is 8 divided by the square root of 21?
1.7457.
Okay, we'll just say 1.75. How about? Okay. So 1.75 is going to be our one critical number where the first derivative was equal to 0. Okay? Give me 1 to 5. Is that all making sense? So we just need test points. What could we use for test points here? 2 and 1. We could. That's fine. We could also use 0 and 10 because they're included in our domain, right? And those are pretty easy ones to use because when we plug those in, the reason I want to use 0 and 10, if I look back at my original function, those are good ones, right? Because like 0 is so easy to plug in, and 10 is going to make that first fraction equal to 0. So those are easy ones to use to evaluate. What is the value of the sign? We don't care about the value. What is the sign of our first derivative at 0? If I plug 0 in, what's that going to give me? T of 0 is going to be 2 plus some positive number. So isn't it going to be positive? Okay. So at 0, we get a positive first derivative. How about at 10? Let's see, at 10, we're going to get, we get positive there too. 10 minus, oh gosh, I'm looking at the wrong one. We're looking at our derivative, duh. We're looking here, right? No wonder, my bad. So if we plug 0 in, we're going to get 0, we're going to get negative, aren't we? Right, because we're evaluating the first derivative. So, yep, that was my mistake. I looked at the wrong function. Everybody see why we're using the first derivative test, right? So we want to be using the t prime row. Okay, so t prime of 0 is, t prime of 0 equals negative, right? Okay. How about t prime of 10? If I plug 10 in, I'm going to get 10 over 2 times the square root of 116. Square root of 116 is going to be like 10 point something very small.
So it's
2 times that is going to be 20 point something very small. 10 over 20 point something is about 1/2-ish, right? Plus negative 1/5, that's going to make it positive. But we could plug it in too, right? But does everybody agree we're going to end up with a positive answer there? This fraction is going to be bigger than that one is, and it's going to be positive. Make sense? So what's that tell us by the first derivative test? If I have a 0 first derivative, what's that tell us? Well, horizontal tangent line. And if we're going from negative derivatives to positive derivatives, what's that look like? Yeah, we're going downhill to going uphill. And so on our domain, there is only one extremum and it's a minimum. So it's got to be the absolute minimum, doesn't it? I mean, we could check the value of the function at 0 and 10, but we know that this is going to be the smallest value, guaranteed. Okay, because we only have one extremum on a continuous function. Okay, make sense?
yeah.
So we found it. We found it. The value that's gonna minimize time is when x is 1.75. So now we got to go back to the problem and answer the question in the context of the problem based on our value of x that we found that minimizes t. So how far upriver should he go to reach his cabinet minimum time then?
Oh wait, sure. This is like X.
Our answer was 1.75 was the value of x that minimized our time function.
So he should go. Is it?
You can say
8.25?
8.25, right? Because 10 minus
He has to go
x, which is
over
1.75.
Oh wait, so you just have to do like
See what I'm saying?
you don't have to start.
So the value of x that we picked, wasn't actually, the value of x represented how much distance, how much he left. How do I say that? It is how far he was left to go along the river when he exited the river, right, and started off cross country, right? So he still had 1.7 miles to go before he reached his 10-mile stretch along the river, which means he must have traveled 8.25. Why so far? Well, because he traveled a lot faster, 2.5 times faster along the river than the land. Okay, make sense? Okay.
Wait, okay, so if it asks, like this one asks, if you were to only go on the rocky part.
Yeah.
then how
Okay,
would you
well,
solve
here we,
that?
well, how come that doesn't work? Well, let's prove it. Like, let's plug in values into our time function. If I were to only go, if I let x equals 0, what would I get? If I let x equals 0, t of 0 would give me 2 plus square root of 16 is 4, so 2 plus 2 is 4. I would have gotten an answer of 4. What if I went all 10? That would give me 0 plus the square root of 116 over 2. But if I go 1.75, that gives us, what's that going to be? I mean, if I plug that into my original function, if I plug in 1.75, what does that give me as a decimal?
Oh, you're kidding. If the plug is what?
1.75.
3.8.
About 3.8, okay. And if I were to plug in square root of 116 over, if I were to plug in 10, I would have gotten the square root of 116 over 2. Square root of 116 is going to be, that's going to give me something like 5.4-ish, slightly less than 5.4. Right, what is that? What's the square root of 116 over 2?
How'd you know it was 5.3?
Well,
That's
this,
crazy.
just
Oh, yeah.
computation.
Something light.
So that is our minimum then, right?